In January 1884, northern Montana was unforgiving. Near the Missouri headquarters, temperatures plummeted to minus 12 degrees Fahrenheit and stayed there for weeks. Jack Reynolds, like every other settler in the territory, had built his cabin according to the prescribed method: thick log walls, a stone fireplace, and a planked floor laid over dirt, standard and supposedly reliable. Yet, by dawn, his neighbor's cabin was a frigid 22 degrees inside, despite burning through 3 cords of wood overnight. Ice formed on the window shutters, a mere 3 feet from the fireplace. Across the high country, homesteaders faced the same losing battle in cabins built, by the book, failing season after season. The settlement committee scoffed when Jack announced his plan to bury a water tank under his floor and connect it to his fireplace with copper tubing. But that brutal winter, Jack quietly implemented his buried tank system, using just 1 cord of wood while keeping his cabin a remarkable 30 degrees warmer than his neighbors on the coldest nights. What did this engineer understand about storing and releasing heat that every frontier builder should have known? Jack Reynolds arrived in the Missouri headquarters area in the spring of 1883, bringing more than just the essentials in his saddlebags. A metallurgical engineer from Illinois, he had spent the previous decade working with foundry steam systems in Chicago. There, he studied the thermosiphon circulation principle patented by British engineer Thomas Fowler in the 1820s. Reynolds grasped how heated water naturally rises through pipes while cooler water sinks, creating circulation without the need for pumps or mechanical force. He had also spent a summer working alongside a Crow Nation timber crew, learning how they dug shallow stone pits next to their lodge hearths to capture heat from the fire and radiate it into the floor throughout the night. However, like every newcomer, Reynolds initially trusted the accepted wisdom of frontier cabin construction. The standard method came directly from United States Army quartermaster manuals distributed at frontier posts throughout the Rocky Mountain territories. Build your cabin in a single weekend using local materials, with thick hand-hewn logs for the walls, a stone and mortar chimney positioned at the center of the long wall, a dirt floor covered with rough planked boards, and a minimal foundation of sill logs laid directly on the ground. The gaps between logs were to be filled with mud and moss. Simple wooden shutters were installed over the windows, with the expectation that thick logs and a steady fire would suffice for the winter. This method prioritized speed and economy, as materials were scarce and time was short before the first hard freeze. Reynolds followed these instructions precisely when he built his cabin that spring, raising it in the same clearing as his neighbors, Tom Miller and the Hendersons. The logs came from lodgepole pines cut just uphill from the building site, each piece carefully hewn to fit snugly against the next. He mortared his chimney stones with clay and sand, laid his floorboards over the dirt, and chinked every gap he could find. The cabin looked solid and well-built, identical to dozens of others scattered across the high country settlements. But that winter exposed the fatal flaws in frontier heating wisdom, flaws that no manual had warned about. During the first serious cold snap in January 1884, when outside temperatures plummeted to minus 12 degrees Fahrenheit and remained there for 6 consecutive nights, Reynolds discovered that his own cabin suffered the same failures as his neighbors. Despite keeping his fire burning robustly until midnight, his floorboards felt icy cold to bare feet by 1 a.m. Drafts whistled up through the gaps between the planks, carrying the chill from the frozen ground directly into the living space. By dawn, frost had formed on the inside of his window shutters, and the air near the ceiling was cold enough to see his breath. His neighbor, Tom Miller, fared even worse in his identical cabin. Miller had burned through 3 full cords of seasoned pine, stoking his fire every 2 hours throughout the night. Yet, his interior temperature still dropped to 22 degrees Fahrenheit by sunrise. Ice coated his ceiling rafters where warm air had risen, condensed, and then frozen solid. His floorboards registered 35 degrees on a mercury thermometer, cold enough to numb feet in seconds. Miller woke each morning with frost coating the inside of his window frames and a bone-deep chill that took hours of fire tending to shake off. Reynolds began studying the problem with an engineer's methodical approach. He measured temperatures at different heights in his cabin, tracked wood consumption against overnight heat retention, and observed how heat moved through his structure. The standard cabin design, he realized, treated heat as something to generate constantly rather than something to store and release gradually. The thick logs absorbed some heat during active burning, but they also conducted that same heat directly to the cold outside air. The dirt floor beneath his planks acted as a massive heat sink, drawing warmth downward into the frozen ground where it disappeared completely. Without thermal mass to capture and hold heat from the fire, the cabin required constant wood feeding to maintain any semblance of warmth. Drawing on his foundry experience and his summer with the Crow timber crews, Reynolds began designing a different approach. The Crow had shown him how they lined shallow pits with river cobbles next to their hearth fires, creating thermal mass that absorbed heat during active burning and radiated it back into the lodge space for hours after the flames died down. His foundry work had taught him how thermosiphon circulation could move heated water through a system using nothing more than natural convection. He had also learned about the German immigrant tradition of massive stone Kachelofen stoves, masonry thermal banks that stored heat in tons of stone and brick, releasing it slowly over 12 to 16-hour cycles. Reynolds envisioned combining these principles into a buried water tank system beneath his cabin floor, connected to his fireplace through copper tubing that would create thermosiphon circulation. Water held roughly 4,000 times more heat per volume than air, making it an ideal storage medium for the intense but brief heat output of a wood fire. By burying the tank beneath his living space, the store heat would radiate upward through the floorboards instead of disappearing into the frozen ground. When Reynolds explained his plan to the settlement committee that spring, the response was immediate mockery. Committee Chairman Robert Hayes dismissed the idea as over-engineering, pointing out that extra iron tanks and copper piping cost real money while wood was free for the cutting. Tom Miller laughed outright, suggesting that Reynolds was trying to build a steam locomotive instead of a simple cabin. The local supply merchant questioned why anyone would haul heavy metal components into the high country when an extra cord of firewood would solve the heating problem for a fraction of the cost and effort. But Reynolds had observed something his neighbors missed. The standard method was not actually solving the heating problem. It was simply masking the problem with massive wood consumption and accepting cold floors, ice-covered windows, and numbing drafts as inevitable frontier hardships. Miller's 3 cords of wood had not kept his cabin warm. They had merely made it barely habitable at enormous cost in labor and fuel. Reynolds suspected that proper heat storage could achieve better comfort with far less wood, but he knew his theory needed testing against the reality of Montana winter conditions. As he began gathering materials for his buried tank experiment, Reynolds understood he was entering uncharted territory. No frontier manual described such heating systems, and no neighbor could offer advice about tank dimensions or insulation strategies. He would need to combine his engineering knowledge with traditional techniques from multiple cultures, then refine the system through direct observation and measurement during the coming winter's trial by cold. Reynolds began construction of his thermal storage system in the late summer of 1884, working with Irish immigrant stonemason Patrick O'Donnell, who had arrived in the territory the previous spring. O'Donnell brought knowledge from County Cork, where his family had embedded iron grain-warming tanks in stone foundations for decades, using thick masonry floors to distribute stored heat through farmhouse living spaces. The Irishman taught Reynolds the critical principle of thermal bridging. Heat stored in buried mass must have a continuous path to the living space above, or it dissipates uselessly into the surrounding soil. O'Donnell showed Reynolds how to excavate the tank pit with sloped sides to prevent cave-ins, digging a space 6 feet long by 3 feet wide by 2 feet deep directly beneath the center of the cabin floor. The Irishman insisted on lining the pit walls with flat stones laid dry, creating an insulating barrier between the iron tank and the surrounding earth. This stone lining would prevent the buried tank from losing its stored heat directly into the cold ground during long winter nights. The tank itself came from a salvaged boiler cylinder that Reynolds modified at the settlement's makeshift forge. He cut inspection ports for cleaning and filling, then welded iron fittings for the copper tubing connections. The finished tank held approximately 60 gallons of water, heavy enough when filled that it required 4 men to lower it into the prepared pit. Reynolds positioned the tank with its longest dimension running parallel to the fireplace wall, maximizing the surface area available for heat absorption and release. The copper tubing installation required precise attention to elevation changes that would drive the thermosiphon circulation. Reynolds ran a 2-inch diameter copper tube from a heat exchanger coil positioned in the firebox down through the floor and into the bottom of the buried tank. A return tube connected the top of the tank back to the firebox at a slightly higher elevation than the supply line. This elevation difference was crucial. Heated water would rise through the supply tube into the tank, while cooler water would sink and flow back through the return line, creating continuous circulation whenever the fire burned. Around the buried tank, O'Donnell supervised the installation of a stone and brick thermal mass floor that would capture heat from the tank's surface and distribute it evenly across the living space. They laid river cobbles in sand around the tank perimeter, then built up layers of flat field stone and salvaged brick, creating a thermal mass that extended 4 feet in every direction from the tank edges. This stone flooring served as a secondary heat storage system, absorbing warmth from the tank during active heating cycles and radiating it back into the cabin air for hours afterward. The insulation strategy came from both O'Donnell's Irish experience and Reynolds's engineering background. Beneath the tank, they placed a thick layer of crushed rock for drainage, then packed clay mixed with chopped straw around the tank sides to prevent heat loss downward into the earth. Above the tank, they installed removable wooden covers that could be lifted for maintenance access, while providing insulation when the system was operating. Reynolds tested the system methodically through the winter of 1884 to 1885, measuring temperatures at multiple points and tracking wood consumption against heating performance. On a typical cold night, he lit his fireplace at 6 p.m., maintaining a robust fire until 10 p.m. The thermosiphon circulation moved heated water continuously through the buried tank, storing thermal energy in the 60 gallons of water and the surrounding stone mass. Temperature measurements revealed the system's effectiveness in ways that surprised even Reynolds. At midnight, 4 hours after banking the fire, his living space air measured 48 degrees Fahrenheit, while his floorboards directly above the tank registered 55 degrees Fahrenheit. By dawn, with no fire burning for 8 hours, the air temperature had dropped only to 39 degrees Fahrenheit, while the floorboards still measured 48 degrees Fahrenheit. The thermal mass was releasing stored heat throughout the night, maintaining floor warmth that radiated upward into the living space. The wood consumption results proved even more dramatic. Reynolds burned just 1 cord of seasoned pine through the entire winter, compared to his neighbor Tom Miller's 3 cords in an identical cabin built to standard specifications. Miller's cabin still experienced the same problems from the previous winter, interior temperatures dropping to 22 degrees by dawn, floorboards measuring 35 degrees, and constant drafts from beneath, despite continuous fire tending. Reynolds documented the thermal performance differences with precise measurements. On the coldest night of that winter, when outside temperatures reached -14 degrees Fahrenheit, his cabin maintained an interior temperature of 39 degrees with floorboards at 48 degrees after 8 hours with no fire. Miller's cabin, despite burning wood continuously, dropped to 28 degrees interior with floorboards at 38 degrees. The buried tank system was keeping Reynolds's cabin 11 degrees warmer, while using 1/3 the fuel. The stone thermal mass flooring provided an additional benefit that Reynolds had not anticipated. The heated stones created radiant warming that felt different from hot air circulation. Standing barefoot on the warm stone floor felt comfortable even when the air temperature was in the low 40s because the radiant heat warmed his body directly rather than relying on heated air convection. This radiant effect meant the cabin felt warmer at lower air temperatures, reducing the fuel needed to achieve comfort. By the spring of 1885, word of Reynolds' system had spread through the settlement. Despite the initial skepticism, Tom Miller visited regularly to measure the floorboard temperatures in Reynolds' cabin, comparing them to his own cold floors. The settlement supply merchant began asking about tank dimensions and copper tubing specifications, sensing potential demand from other settlers facing similar heating challenges. Reynolds refined the system through that first winter, adjusting the circulation rate by modifying the copper tube routing and experimenting with different firing schedules to maximize heat storage efficiency. He discovered that building a hot fire for 4 hours stored more usable heat than maintaining a moderate fire for 8 hours because the higher water temperatures achieved greater thermal storage density in the tank mass. The success of the buried tank system validated Reynolds's engineering approach, but it also revealed new challenges. The system worked well for foundation-level heat storage and release, but heat was still escaping through the cabin's log walls and roof. Reynolds began planning modifications to the building envelope that would capture and retain the heat his buried system was generating, setting the stage for further improvements to his integrated heating approach. During the second winter of operating his buried tank system, Reynolds discovered that storing heat beneath the floor solved only part of his cabin's thermal problems. While his stone floor remained comfortably warm throughout the night, heat was escaping rapidly through the log walls and roof, creating temperature gradients that wasted the energy his tank system captured. On particularly cold nights in January of 1886, Reynolds measured ceiling air temperatures dropping to 25 degrees Fahrenheit, while his floor registered a comfortable 53 degrees Fahrenheit. Ice formed on the interior surface of his ceiling rafters where warm air rose and condensed against the cold wood, then froze solid. Worse, condensation gathered on the log wall, where heated air contacted the cold exterior-facing surface, creating moisture problems that threatened the structural integrity of his logs. These observations led Reynolds to seek out Hans Lindström, a Swedish immigrant carpenter who had settled in the Bitterroot Valley the previous spring. Lindström brought old-world knowledge of log construction techniques developed in Scandinavia's harsh winters, where builders had refined double-chinking methods over centuries of experience. The Swede explained that single chinking, the standard frontier practice of jamming mud and moss between logs, left microscopic gaps that allowed air infiltration and heat loss. Scandinavian builders used a double chinking system that sealed logs with two distinct layers, a primary seal of lime clay sand mixture pressed deep into the log gaps, followed by a secondary outer seal of lime mortar that hardened into a weather-resistant barrier. Lindström demonstrated the lime-clay mixture preparation, combining quicklime with local clay soil and sharp sand in a ratio of 1 part lime to 2 parts clay to 3 parts sand. The quicklime reacted chemically with water to create calcium hydroxide, which bonded with the clay particles to form a plastic, durable seal that expanded and contracted with the logs without cracking. The sharp sand provided aggregate structure that prevented shrinkage as the mixture dried. This double chinking system required removing all existing mud from between Reynolds's logs, cleaning the wood surfaces, and rebuilding the seal system from scratch during the warmer months. The roof thermal barrier came from knowledge Reynolds gained through a chance encounter with a Yakama Nation basket maker who had worked on construction crews in the Pacific Northwest. The Yakama builder explained how their traditional longhouses used thick moss and sod layers over cedar plank roofing to create thermal mass above the living space. Unlike simple wood shingles that conducted heat rapidly to the outside air, the sod layer absorbed heat during the day and released it slowly overnight, reducing heat loss through the roof and moderating temperature swings in the space below. Reynolds modified this technique for his log cabin by installing riven cedar planks as roof sheathing over his existing log rafters, then building up a 4-inch thick layer of moss, grass sod, and packed earth over the cedar base. The cedar planks provided a solid foundation that could support the weight of the sod layer while creating an air gap between the thermal mass and the structural roof timbers. The sod layer itself became a secondary thermal storage system, absorbing heat that would otherwise escape through the roof and radiating it back down into the cabin during cold nights. The interior wall treatment drew on advice from old Sam Whitaker, a local frontier builder who had experimented with interior plasters in his stone ranch house. Whitaker had discovered that coating log walls with mud and horsehair plaster increased the heat storage capacity of the wall surfaces while providing a smoother interior finish that reflected radiant heat more effectively than rough log surfaces. The plaster mixture combined local clay soil with chopped horsehair as reinforcing fiber, creating a coating that adhered well to log surfaces and provided additional thermal mass inside the heated space. Reynolds applied these 3 envelope improvements systematically during the summer of 1886, working section by section to avoid compromising the cabin's weather protection. He began with the double chinking, removing old mud from between logs and cleaning each joint down to bare wood before applying the lime clay sand mixture. The primary chinking required pressing the mixture deep into the gaps using wooden tools, ensuring complete contact with both log surfaces. After the primary seal cured for 2 weeks, Reynolds applied the lime mortar outer layer, smoothing it flush with the log faces to create a uniform exterior surface. The roof modification proved more challenging because it required supporting the weight of the sod layer without overloading the existing log rafters. Reynolds installed additional support posts at the cabin centerline, then laid the ribbon cedar planks with slight gaps between them to allow air circulation while supporting the thermal mass above. He harvested moss from nearby creek banks, cut sod blocks from upland meadows, and built up the roof layer gradually, watering it during installation to ensure good compaction and root establishment. The interior plaster application required careful timing to ensure proper adhesion to the log surfaces. Reynolds mixed clay soil with water to create a workable paste, then added chopped horsehair and stirred the mixture until the fibers distributed evenly. He applied the plaster in 2 coats, a rough base coat pressed into the log surface irregularities, followed by a smooth finish coat that created an even interior wall surface. The horsehair reinforcement prevented cracking as the plaster dried and provided long-term durability. Testing the improved envelope during the winter of 1886 to 1887 revealed dramatic performance improvements. On a night when outside temperatures dropped to -14 degrees Fahrenheit, Reynolds measured ceiling air temperatures of 46 degrees compared to the previous winter's 25 degrees. His floor temperature remained at 53 degrees, showing that the buried tank system continued working effectively, while the improved envelope retained more of its heat output. The elimination of condensation problems proved equally important for long-term cabin durability, with better chinking and interior plaster. Warm interior air no longer contacted cold log surfaces directly, preventing the moisture formation that had threatened his wall structure. The sod roof eliminated the ceiling rafter icing that had been a persistent problem while adding thermal mass that moderated temperature swings throughout the cabin interior. Wood consumption dropped further as the envelope improvements took effect. Reynolds now burned just 4/5 of a cord through the winter compared to his previous winter's single cord consumption. The buried tank system was storing the same amount of heat, but the improved envelope was retaining that heat longer, reducing the frequency of firing cycles needed to maintain comfort. The integration of thermal storage and heat retention created a synergistic effect that exceeded the sum of the individual improvements. Heat generated by the fire was captured in the buried tank, retained by the double-chinked walls and sod roof, and distributed evenly through the interior space by the plaster wall surfaces and heated stone floor. Reynolds had created a complete thermal system that managed heat generation, storage, retention, and distribution as integrated functions rather than separate problems requiring separate solutions. By late winter of 1887, Reynolds had created a new problem through the success of his thermal storage and envelope systems. On sunny March days, when outside temperatures climbed to 38 degrees Fahrenheit, his cabin interior soared to 72 degrees by mid-afternoon as solar heat combined with a continued output from his buried tank system. The improved envelope that had solved his winter heat retention problems now trapped excess heat during transitional seasons, creating stifling conditions that made the cabin unbearable during warm weather periods. Worse, the effective thermal mass meant his buried tank continued radiating stored heat well into the evening, keeping interior temperatures uncomfortably high even after outside air had cooled to the 50s. The overheating created a cascade of secondary problems that threatened the cabin's habitability during shoulder seasons. Condensation formed on his interior plaster walls where warm, humid air contacted cooler surfaces near the windows and door frames. This moisture accumulation encouraged mildew growth that stained his carefully applied wall finish and created musty odors throughout the living space. The sealed envelope that prevented winter heat loss also blocked natural air circulation, leaving the cabin stuffy and oxygen depleted after Reynolds spent long spring evenings working indoors on equipment maintenance and planning. These ventilation challenges led Reynolds to consult with Pat O'Sullivan, a Cornish tin mine engineer who had immigrated to the Montana Territory after mining operations in Cornwall shut down. O'Sullivan brought underground ventilation knowledge developed in the deep mines of southwestern England, where crews had perfected methods for moving fresh air through confined spaces without losing thermal control. The Cornish man explained the principle of earth tube preconditioning, a technique where incoming air passed through buried passages that moderated its temperature before entering the workspace. O'Sullivan demonstrated how to construct an earth tube air intake that would provide controlled fresh air without compromising the cabin's thermal performance. The system required digging a narrow trench from a point 20 feet uphill from the cabin down to the fireplace foundation, sloping gently to ensure proper drainage. Reynolds lined this trench with stone slabs to create a crude tunnel, then installed a 4-inch diameter iron pipe that connected to an adjustable damper at the base of his chimney. Incoming air would travel through this underground passage, reaching nearly ground temperature before entering the fireplace, where it could be heated gradually without creating drafts or sudden temperature changes. The earth tube installation proved more complex than O'Sullivan had initially described. Reynolds had to excavate through rocky soil and around tree roots, maintaining proper slope while ensuring the pipe. The joints of the underground tank remained airtight, preventing any groundwater from seeping in. Reynolds strategically placed intake vents at the uphill end, equipped with adjustable covers to fine-tune airflow. This allowed him to precisely control the amount of fresh air entering the system, adapting to both interior conditions and prevailing weather patterns. Essential to the system was a condensation drain installed at the lowest point of the underground run, which prevented moisture buildup that could potentially obstruct airflow or even freeze during colder periods. The inspiration for the thermal release controls stemmed from a conversation Reynolds had with Joseph Winamica, a builder from Pott who was involved in construction projects in the Bitterroot Valley. Winamica shared insights into the traditional desert lodges of his people, which utilized automatic ventilation systems. These systems would open and close based on the interior temperature, effectively preventing overheating during the scorching days while conserving warmth during cooler nights. These ingenious structures relied on simple mechanical principles to create a self-regulating airflow, eliminating the need for constant manual adjustments. Reynolds ingeniously adapted this concept by installing a thermal release vent directly in his floor, positioned above the buried tank. He fashioned a hinged wooden flap that would automatically open when floor temperatures exceeded a predetermined level. This allowed excess heat emanating from the tank to escape into the crawl space beneath the cabin, preventing it from further warming the interior air. The mechanism employed a simple bimetallic strip composed of two different metals bonded together. As temperatures rose, the strip would bend, triggering the vent to open. This system effectively prevented overheating while still preserving the tank's heating capacity for cooler periods. The seasonal bypass system emerged from discussions with Mary Ellis, the local blacksmith and inventor, who had previously assisted Reynolds with damper designs. Ellis had been experimenting with dual-purpose heating systems that could perform different functions based on the season, maximizing the value of costly metal components and complex installations. She proposed routing Reynolds's thermosiphon circulation through a secondary, external tank during the warmer months. This would allow the buried system to function as a solar water heater for domestic use, rather than continuously heating the cabin's interior. Ellis played a key role in helping Reynolds construct the bypass valving system, utilizing salvaged materials from abandoned mining equipment. The system incorporated manually operated gate valves to redirect the thermosiphon flow from the interior buried tank to an external iron tank strategically placed in a sunny location outside the cabin. During the spring and summer months, Reynolds could close the interior circulation loop and open the external loop, allowing his fireplace to efficiently heat water for washing and cooking while simultaneously preventing unwanted heat buildup inside the living space. The external tank effectively absorbed solar heat on sunny days, providing a sustainable source of warm water without consuming any fuel. Reynolds rigorously tested these ventilation and control systems throughout the spring of 1887, carefully monitoring their performance as weather conditions shifted. The earth tube air intake immediately proved its effectiveness in delivering fresh air without causing thermal shock. On a typical warm afternoon, outside air at 70 degrees Fahrenheit would cool to approximately 60 degrees as it passed through the underground pipe, then gradually warm to room temperature after entering the fireplace area. This preconditioning effectively eliminated the drafts and temperature fluctuations that had made opening windows or doors uncomfortable during periods of transitional weather. The automatic thermal release vent successfully prevented the overheating episodes that had plagued the cabin during the previous spring. When interior floor temperatures exceeded 65 degrees Fahrenheit, the bimetallic trigger would activate the floor vent, allowing excess heat to escape while maintaining comfortable air temperatures. Reynolds measured peak interior temperatures of 68 degrees on days when, in the previous year, temperatures had reached uncomfortable levels above 72 degrees. The system maintained thermal comfort without requiring constant monitoring or manual adjustments. The seasonal bypass system proved equally beneficial in extending the utility of Reynolds's investment in thermal infrastructure. During the summer months, he routinely produced 15 gallons of heated water daily through passive solar collection, providing warm water for personal washing, laundry, and equipment cleaning without burning any wood or overheating his living space. The external tank reached temperatures of 90 degrees Fahrenheit on sunny days, which was sufficient for most domestic purposes. Wood consumption during the transitional season dropped to 0.8 of a cord for the entire spring period, compared to neighbor Tom Miller's consumption of 1.5 cords during the same time frame. Miller's standard cabin continued to suffer from the same overheating and stuffiness problems that Reynolds had successfully addressed, while also requiring continued wood burning to maintain adequate heating during cool spring evenings. The integration of controlled ventilation with thermal storage and envelope systems created a year-round heating and cooling solution that automatically adapted to changing weather conditions. Reynolds had transformed his cabin from a simple shelter that required constant fire tending into a sophisticated thermal management system that provided comfort across all seasons with minimal fuel consumption and human intervention. The winter of 1887 presented conditions that would push every heating system in the northern Montana Territory to its absolute limit. A persistent high-pressure ridge trapped Arctic air over the region for 10 consecutive nights, with temperatures averaging -8 degrees Fahrenheit and sustained winds of 15 miles per hour, which drove the effective temperature far below anything settlers had experienced since arriving in the territory. 3 feet of snow accumulated over a 2-week period, effectively isolating homesteads and making wood gathering nearly impossible. Many families relocated to root cellars or shared accommodations in the sturdiest buildings within their settlements, abandoning their cabins until the weather improved. Reynolds faced this ordeal with a heating system that had been refined over 4 years, incorporating thermal storage, envelope sealing, and ventilation control into a comprehensive approach that treated heat as a renewable resource rather than simply consuming it as quickly as it could be generated. His buried tank remained at its full 60-gallon capacity. The sod roof had matured into a thick, insulating layer, and his earth tube air intake was capable of delivering fresh air without thermal shock, even in the extreme cold. The true test would be whether these integrated systems could maintain habitability during sustained, extreme conditions that overwhelmed simpler approaches. Tom Miller's cabin, still built to standard frontier specifications, required an immense amount of fuel simply to prevent freezing. Miller burned through 5 full cords of seasoned pine during the 10-night cold snap, feeding his fireplace every 2 hours around the clock to maintain some semblance of interior warmth. Despite this constant fuel consumption, his interior temperature plummeted to 25 degrees Fahrenheit by dawn on the coldest night, while his floorboards registered a mere 35 degrees. Frost coated his interior window frames. Ice formed on his ceiling rafters where warm air condensed and froze, and one of his chinking logs cracked due to repeated freeze-thaw cycles. The constant high heat also caused chimney problems, as rapid temperature changes led to cracks in his stone and mortar chimney, allowing smoke to leak into the cabin. The Henderson family, neighbors in another standard cabin, fared slightly better through more efficient fire management, but still burned 4.5 cords of wood during the same period. Their interior low temperature reached 28 degrees on the worst night, with floorboards registering 38 degrees. Ice droplets formed along their roof eaves where interior moisture froze, and one wall log developed a visible crack that required immediate chinking repair to prevent further heat loss. The Henderson cabin also experienced chimney frost problems that temporarily blocked the flue, forcing them to modify their firing schedule to prevent dangerous smoke accumulation. Reynolds's integrated system performed with remarkable stability throughout the extreme weather period. His total wood consumption for the 10-night trial was just 1¼ cords, less than 1/4 of his neighbor's fuel requirements. On the coldest night, when outside temperatures reached -22 degrees Fahrenheit with wind gusts of 25 miles per hour, his interior air temperature measured 55 degrees at dawn, while his floorboards registered 62 degrees. The buried tank system continued to store and release heat in regular cycles, moderated by the earth tube air intake that provided fresh air pre-warmed to approximately ground temperature before it entered the heating circulation. The performance difference extended beyond simple temperature maintenance to overall system reliability and occupant comfort. Reynolds experienced no structural damage, no chimney problems, and no interior frost formation during the entire cold period. His automatic thermal release system prevented overheating during sunny daytime periods when solar gain combined with stored tank heat, while the earth tube intake eliminated the drafts and temperature shocks that plagued cabins relying on simple door or window ventilation. Most significantly, the radiant heat from his heated stone floor created comfortable conditions at lower air temperatures, allowing him to maintain his normal activities and sleep patterns throughout the crisis. The mathematical precision of Reynolds's fuel savings became apparent when the settlement committee documented heating costs across the community. Miller's 5 cords of wood represented approximately 40 days of cutting, splitting, and hauling labor, valued at nearly $30 in 1887 currency, when labor shortages drove woodcutting wages to 75 cents per day. Reynolds's 1¼ cords required just 10 days of wood preparation labor, saving $22 in direct costs while providing superior comfort and reliability. The durability trial revealed another advantage of Reynolds's systematic approach over conventional frontier heating. Miller's cabin required immediate chimney repairs costing $8 in materials and labor, plus the replacement of cracked chinking that took 3 days of work. The Henderson cabin needed similar chimney maintenance and log repairs. Reynolds's cabin emerged from the extreme weather period with no structural damage and no maintenance requirements beyond routine ash removal and copper pipe inspection. The community began to take serious notice of Reynolds's methods. As word spread through the settlement about the performance differences during the harsh winter, Robert Hayes, chairman of the settlement committee, who had initially dismissed Reynolds's buried tank concept as overengineering, visited the cabin repeatedly during the cold snap to verify the temperature measurements and observe the system's operation. Hayes documented his findings in detailed notes that became the foundation for the settlement's official heating recommendations. By the spring of 1888, 3 other families in the settlement had requested detailed drawings of Reynolds's thermal storage system. The local supply merchant began stocking copper tubing and iron tank materials, anticipating demand from settlers who had witnessed the fuel savings and comfort advantages. Mary Ellis, the blacksmith who had helped Reynolds develop his ventilation controls, began fabricating similar thermal release mechanisms and seasonal bypass valving for other customers. The Settlement Committee's 1892 Homestead Heating Options publication featured Reynolds's integrated approach as a recommended alternative to standard log cabin heating, complete with construction diagrams and material specifications. The publication noted that cabins built using Reynolds's methods typically consumed 60 to 70% less fuel, while providing superior comfort and requiring less maintenance than conventional designs. This official endorsement marked the transition of Reynolds's innovations from individual experiment to accepted frontier building practice. The long-term performance of Reynolds's original installation provided additional validation of the systematic approach. 8 years after the initial construction, the buried tank showed no signs of corrosion or leakage. The thermosiphon circulation continued to operate reliably, and the sod roof had developed into a mature ecosystem that provided excellent insulation while requiring no maintenance. The cabin maintained its superior heating performance throughout this period, while conventional cabins in the settlement required regular chinking repairs, chimney rebuilding, and increased fuel consumption as their structures aged and developed gaps. The influence of Reynolds's work extended beyond the immediate settlement as traveling craftsmen and itinerant builders observed the techniques and carried them to other frontier communities. By the early 1900s, Building manuals for cold climate construction included references to thermal mass storage and integrated envelope sealing based on principles that Reynolds had demonstrated in the Montana High Country. Modern passive solar and thermal mass construction techniques trace their lineage directly to innovations like Reynolds's buried tank system, validated by the same principles of heat storage, controlled release, and systematic integration that proved their worth during the brutal winter of 1887.